Awesome. So, hello, my name is Hannah Bradley. I'm a recent graduate from Oakland University, and today I'm going to be talking about directed graph neural networks with antiferromagnetic artificial neurons. So first, why are we using antiferromagnets? Well, ferromagnetic materials have a parallel spin pattern, where all their electron spins point in the same direction. But antiferromagnets have an alternating spin pattern, which allows them to work at much higher frequencies. These frequencies can be excited by a spin current applying torque to the magnetic sublattices, which tilts the spins in the same direction. In ferromagnets, the angle between the spins stays the same because they're parallel. But in antiferromagnets, the angle between the spins changes, which allows antiferromagnets to work at terahertz frequencies compared to the gigahertz of ferromagnets. This means we can use AFM materials to create very fast devices. We start by creating an AFM spin Hall oscillator by laying a piece of antiferromagnet on top of a piece of platinum. A charge current in the platinum will cause a spin current in the AFM by the spin Hall effect. The spin current acts on both magnetic sublattices, causing them to rotate. But by using biaxial anisotropy AFM, this rotation is not uniform in time. The rotating spins create a spin pumping signal, the magnitude of which is proportional to the rotational speed. This non-uniform rotation at a terahertz frequency results in a sequence of very intense, very short spin pumping spikes. The orientation of the AFM sublattices can be described by using this angle phi, which is the angle between the Neal vector and the z-axis. The derived equation for phi resembles the equation of a mechanical pendulum under a driving force, which means each turn describes a physical effect with a mechanical analogy. The spin torque serves as the external force which drives the rotation. But the most interesting part of this equation is that the exchange energy contributes an effective mass, which means the oscillator now has inertia. The oscillator now acts as an inertial particle under a driving force, with the driving force being the spin torque from the spin current. When the current is at a supercritical level, the AFM will act as an auto-oscillator, continuously outputting spin-pumping spikes. But let's consider the case where the driving force is at a subcritical level, and the spin current alone is not enough to send it into an oscillation. With an additional pulse of current, the oscillator can act as a neuron, overcoming the energy barrier and causing a single oscillation. At the bottom of this sinusoidal path, the change in the angle phi is the fastest, which results in this output spike due to spin pumping. Plots like these that show those output voltage spikes are the results of my simulations. Due to the terahertz properties of AFM materials, the width of this output spike is on order of picoseconds. This is incredibly fast, and for comparison, the biological neurons in your body work on a millisecond time scale. So now the oscillator can act as a very fast artificial neuron, always ready to go and to be set off by an external signal. They are unlike conventional artificial neurons because of this inertia. We need to be able to connect AFM neurons together such that they can be set off by one another. In our simulations, we just use an arbitrary coupling matrix to determine the strength of coupling between the neurons. Linking up multiple AFM neurons in chain allows the output of one neuron to act as the input for the next. In conventional artificial neurons, there's an immediate reaction and result of an input. But the inertia in AFM neurons causes there to be this delay between a neuron receiving input and the resulting output. So now we have AFM neurons and we can link them together. The next step would be to start building neural networks capable of more complex functions, such as pattern recognition. For example, you can clearly see that this is a picture of a dog. My pattern recognition works perfectly. Because AFM neurons are very different than conventional artificial neurons, we can ask the question, are we still able to use standard machine learning algorithms to train them? In a recent paper that legitimately just got published last week, we trained AFM neurons for pattern recognition using this supervised learning algorithm called Spike Pattern Association Neuron, or SPAN. The SPAN algorithm uses the difference between the actual spike time of the neuron and the desired spike time to update the weights. The use of this SPAN algorithm resulted in a one-layer neural network with a single output neuron that was able to recognize symbols by outputting a spike at a target time. This was the first example of training AFM neurons for pattern recognition. However, the simplicity of the SPAN algorithm limits the computational capability of this resulting one-layer neural network. So in order to further the study of AFM neurons and AFM neural networks, we need to replace it with a more complex learning algorithm. This new algorithm is going to be based on the popular backpropagation algorithm for multi-layer neural networks. During backpropagation, inputs are processed by a feed-forward neural network. So first the inputs are excited, and then they travel towards the outputs. Once the inputs reach the outputs, an error or loss function is calculated from the difference between the actual outputs and the target outputs. Then a process called gradient descent is used to update the weights between neurons. During gradient descent, the gradient of the error is used to minimize the loss function. The weights are then updated, starting with the output layer and traveling backwards through the neural network, hence the name backpropagation. For our learning algorithm, we're going to be using the fire rate of the output neurons to calculate the error. Then, a least mean squared error is found from the difference between the actual fire rate of the output neuron and the target fire rate. And then finally, we use gradient descent to find the change in synaptic weights between neurons in the neural network. So now that we have our gradient descent algorithm, we can start using it to train multi-layer AFM neural networks for pattern recognition. To first ensure that our gradient descent algorithm works with AFM neurons, we build a simple two-layer neural network. This neural network has 4 input neurons, 10 hidden neurons, and 4 output neurons. And each layer is fully connected to the previous layer via trainable weights. The patterns we're going to be using in training are a binary spiking pattern that spans the 4 input neurons. A 1 in the patterns means the associated input neuron fires a single spike within a certain time window, and a 0 means the neuron does not fire. During training, the gradient descent algorithm is used to find the change in weights for both the input layer and the output layer in order to minimize the overall error of the neural network. This two-layer neural network is trained on 4 patterns for each of the 4 output neurons. The accuracy of the neural network is tested using variations of these 4 patterns, where the variation comes from changing the timing of the input spikes. This neural network achieves a 100% recognition rate in about 400 epochs, which translates to 150 nanoseconds of real time. This is incredibly fast and due to the terahertz properties of AFM neurons, highlighting one of the advantages of using AFM materials. It should be noted that 2 of the patterns used in training have the same number of total spikes. This shows how it's not just the fire rate or the count of spikes that's being recognized, but rather the exact pattern over the 4 input neurons. This simple 2-layer neural network allows us to show that we can use gradient descent to train AFM neurons, but its functions are limited due to its simplicity. Mainly, this neural network doesn't have any lasting memory, which is something that's really important in big neural networks. And it has no lasting memory because the inputs all arrive at the outputs at relatively the same time after passing through this hidden layer. On top of that, this network doesn't use any unique features of AFM neurons. In order to build a neural network that does use the unique properties of AFM neurons, we alter the design of the hidden layer. In this new neural network, the hidden layer takes the form of a directed graph. hidden neurons are randomly connected to other hidden neurons in such a way that the neural network remains in a feed-forward design, meaning there's no looping or backwards connections. So the signals always travel towards the outputs. This graph layer introduces different lengths of delay between inputs and outputs. Some connections might be short, while others may need to travel through many hidden neurons. This results in a working short-term memory that I'll illustrate in a few slides. The inputs of this neural network are reduced from 4 neurons to 2 neurons using sequential binary encoding. An input neuron might spike once or twice, forming a pattern of up to 4 spikes that overlap in time. Again, during training, the gradient descent algorithm is used to update the weights for all 3 layers in order to minimize the error. However, with this neural network, we run into an issue with the outputs after training. Mainly, we observe that in reaction to an input pattern, more than one output fires. To counteract this effect, we take advantage of the unique inertial properties of AFM neurons. This inhibitor circuit allows us to inhibit the output of an AFM neuron. In the first case, we see a single input causes these 2 blue neurons to fire at relatively the same time, causing a strong enough kick the output neuron needs to fire. But in the second case, the red inhibitory spike shortens the delay of one of the blue neurons. Now, the output neuron does not receive the 2 signals at the same time and is suppressed. This kind of inhibition, where 2 inputs equals 0 outputs, is only possible due to the inertia of AFM neurons, which means this kind of inhibition is impossible with conventional inertialess neuromorphic circuits. We now include this inhibitor circuit to the outputs of the graph neural network to ensure only the first output to spike is recorded while the others are suppressed. This is commonly referred to as a winner-takes-all output, and the weights of this winner-takes-all output circuit are fixed and not altered during training. The main feature of this graph neural network is that it has a working memory. This can be illustrated if we look at the outputs at different times during training. Panel A shows the input pattern 1, 1, 1, 1, where both inputs spike twice in an overlapping sequence in time. Panel B shows how the outputs react at the beginning of training, and we can see that they react randomly, with some outputs even spiking before the inputs have finished. This is due to ultra-short connections between inputs and outputs in the graph hidden layer. But as training progresses, we see that the outputs are being pushed later in time. This gives the neural network time to fully process the inputs before the outputs react. And at the end of training, in panel D, only a single output spikes well after the inputs have finished, indicating the pattern was recognized.
Anna,
This neural
can you
network,
please wrap up, please, the presentation?
Yeah, we got 2 slides.
Okay.
So this neural network achieves 100% recognition rate for these 3 patterns in 450 epochs, which is about 350 nanoseconds of real time. And just like the 2-layer neural network, we are using patterns that have the same number of total spikes to make sure the neural network is recognizing the difference between patterns with the same count of spikes. So in summary, we can use antiferromagnetic materials and their terahertz properties to create ultra-fast neurons with an effective inertia. We use a backpropagation algorithm with gradient descent in order to train these big multi-layer AFM neural networks. And finally, the directed graph neural network with this special winner-takes-all output layer uses the inertial properties of AFM neurons to achieve 100% recognition rate. Thank you very much.
Thank you very much for your nice talk, Anna. I think we don't have any time for questions. Maybe if you have any questions for Anna, maybe on Gather Town, you can start some discussions.